Did you, I can't remember, did you have any case studies to go through, or were you was it just purely for people working on their own codes? I can't quite remember where we left it, sorry.
I think it's best for people to work on their own codes at this point, and if they have specific questions, then we might go to one of the case studies, but it's better that we get some measurements and can look at the analysis of your codes, even if it's just one or two. I think Elisabetta and who was it? Irina, perhaps. There was at least a couple of people who had measurements already from yesterday. I mean, not from today.
Was it Elisabetta that had the? I can't remember. I can't quite remember the names. Whether it was Irina or that Elisabetta had.
iPad 3D with the boundary exchange, the ghost exchange.
Yeah, the plasma code. Yeah, fine.
Yeah, hi. It's me, Elisabetta. Yeah, I actually have a question, but I need to retrieve 1 second the file, because I after we closed the conversation yesterday, I tried to filter it, and even with only like filtering a function, I get something which is very massive. Let me just remember how to check this file. Okay.
I made you a presenter, so you should be able to share stuff if you want now.
Yeah, I was just to ask if this is something, if I should, yeah, I get something with 14 gigabyte that requires 14 gigabyte. Is this too much, isn't it?
That's the total, or is that per process?
In the line estimated memory requirements.
It's per process.
It's per process, okay. So
14 gigabytes is too much per process.
So estimated memory requirements, in the line estimated memory requirements, this is what I get for process.
Yes.
Okay, and so it is a bit a lot, but I'm tracking only one function. Then I'm doing something wrong, probably.
If you could share the score p-score output, then we can see what's going on.
Yeah, yeah, I'm going to share the screen. Okay. Okay. Okay, so this is my filter file. I wanted to exclude this MPI thingy, but it doesn't work.
Yeah, that doesn't make sense. I'm not sure what you want to do with it, but it doesn't make sense. So.
Okay.
And
okay.
Exclude star, include. So your intention was to just include the two things that match, add mass and compute moments?
Yeah.
Okay. But you can remove that line that says MPI filter. I mean, that won't do anything.
Okay, because, okay.
So that's
in
the last line, so there is an S missing. It's missing. It should read score P region names end. So the S at the beginning.
Okay, I copied it wrong then. Okay.
That also won't make any difference.
I think it worked anyhow, because it produced something.
Yes, I mean that last line would be treated as a function, but it doesn't exist, so it would be ignored.
Okay, and now when I do, oh, I need to check the slide for the command. Or you can tell me what is the command already to get like the I want to see this score score P a score, but with all the function is -r, right?
Correct. With the R is for all of the routines.
For minus R profile dot index. And then if I do it like this, it will, and no, then it's not this one that I want. There is something that it shows you like
So this seems to be have done what you have asked it to do. You're keeping add mass, and you're keeping compute moments, and you have all of the MPI you get automatically. So that's why the filtering wouldn't have had
okay.
any effect on the MPI. But most of your requirements are for this add mass routine. That's where your 14 gigabytes are coming from.
Okay, so I should not probably trace this one.
Is
You
that
should
because it's
definitely
being,
not.
is that the one that's being called a huge number of times? Is that the point?
It's been called 150 billion times, yes.
Okay,
For
that's
each time
quite
it's called, we have to record beginning, enter, timestamps, and that mounts up. 150 billion times is a lot.
good job you use 64-bit integers for that. Otherwise, you'd not be able to.
Because this is called for every particle. That's why so much.
But why did you want to keep that?
It was because when I look at the time fraction, so
You
if
maybe
I
want
go,
to just trace the. I don't know how many functions call that function, but if there's a wrapper function that calls it, that might be the one to trace. You see what I mean? Where is it
and I
called?
went
What?
here and check and do the same with this one. Look at this. Yeah, so this one was 30%. This is the one not filtered yet. And then the other one that I wanted to track was another big percentage, like, yeah, 27%.
So for the second one, it's looking entirely reasonable, but for the add mass, it's completely unreasonable. So that's definitely one to be filtered out. I mean, it depends what the goal is. If the goal is to understand the performance, then there's no way of tracing 150 billion instances of it and making any sense of that.
Okay, so I should filter out also this one. It was that I was looking at where the code at this time percentage, where the code was spending most of its time. But yeah, maybe.
But a lot of that time is actually going to be the overhead of going in and out of the measurement for the beginning and end of that function. So it's not really that time. That's the elevated time or the dilated time because of the 150 billion calls to measure it.
Okay, then I try to redo it, just filtering that one, and then I try to apply what we did today with the square.
Do you know where that function is? I can't see it anywhere in the source. I must be doing something.
This is not, because this is not this is not iPic. This is what I'm profiling is XTB. It derives from iPic, but it implements a slightly different algorithm.
Fine.
But David is right. Can we take a look at the cube file where we're seeing this function? So the one where this original measurement is?
The original one.
Yes, I mean,
yeah, okay.
Yeah, the original one.
Because this won't work, so I need to. I don't know why after a while it stopped forwarding the X window, so I need to.
On a Mac. Yeah, Mac seem to sometimes have some timeout. We've seen that before. They just seem to time out after. I don't know. an hour or something. I don't know.
No. Okay. So now I just do the original one we want to see.
Yes.
And this will be cube. Why didn't work now? Did I have it open somewhere? No.
Do you normally need to do the SSH minus X or?
It should be in the config, but maybe I forgot to put in the config because I'm using a shortcut. Yes, but maybe I forgot to put it in the config. Big. Let me exit and re-enter again. No, I don't know. I get this error now, which I didn't get before. Let's try to see if it works. Well, no, it's not. Let me try another thing. How I get this, which I didn't used to get. What is happening now?
What's happening though? When you can you, what is it refusing to do X? No.
Yes, X is failing.
I got exactly the same thing. I just got kicked from X. I couldn't launch the cube, and now I relogged just like her and got the same.
What the hell is that? Can you do?
So I got it the first time I log in, and then yesterday. But then like I log off and log in again, and it disappeared. But now it seems that it.
Try that. So yeah, try that. What's that? Oh, I put in the chat. So I have no idea what the sexual authority N is. I mean, it's bonkers. Why is it suddenly? I would remove both
Maybe
of them.
remove this file.
Remove both of them. Well, remove the
Yeah.
X authority. Remove both of them.
Oh.
Dot X. It's twiddle slash dot. Yeah, star. Remove them all. Okay, right. Log out and back in again. Try. Okay, we can try it. Okay.
No.
That's fine. Well,
That's fine. That's what we expect. You should create it
Ah,
the first time.
Okay.
you don't need to exit. You don't need to exit. It created. Do the ls again. It will have created it. So that's not an error. It is just saying the file doesn't exist, but it's created.
Okay.
Yeah. It should be fine now. I don't know what the heck happened there.
Okay.
So,
No, there it is. Yeah, now it should work.
So for some reason, it didn't know what it was doing. I don't know what the heck it was doing now, but anyway. So I guess, Brian, you're going to try and find out who is calling AddMass. Is that your...
Exactly. Go into the middle pane and then do a Control F or the right click to bring up the menu to find. If you're on a Mac, a right click is probably awkward, so Control F is maybe easier.
No, but yeah,
Add something or other. AddMass. Okay. Yeah. You need to select it from that menu that appeared. You would select it. Oh well, that's worked anyway. So that's the only place that it's called. And if you were to lose that information about it being called there, all of the time will be shown inside compute moments, which is fine because compute moments is also
is what I wanted to track.
So all of that content of compute moments is completely computational. There's no MPI in there.
Okay.
So just while we're here, so you have AddMass selected. Go into the right-hand pane and open up the statistics, I guess. Okay. So that's showing the variation of the time across the different processes from 65 to 76 seconds. Yeah. So some are taking a bit more, some are taking a bit less. Do you understand that box?
Hello?
Do you understand the box, what is showing there with the lines from 65 to 76 seconds?
Is that maximum and minimum?
Yeah, the for each process.
So the range of values across the processes, yes. So there is some variation there. It's a good 10% and more. Now, can we select the visits from the left-hand side, the left-hand pane, the visits metric? So there's a variation in the visits metric as well. It's not so large. It's actually a very small variation there.
Tiny.
It's hard to see the variation, so that's why I would probably go into the right-hand side and at the very top change absolute to pure percent. So that's showing you how tiny it is. You can't really distinguish it. But there is a noticeable distinction in the amount of time that they take. So if we go back to time, we'll see that the time is varying quite a bit. Yeah.
Yeah.
And if we go to topologies, we can try and see changes across the process, which processes have high values, which have low, but it looks like a fairly modal distribution to me.
I think it depends on because this is a function on the particles, and each process might have a different number of particles to deal with. So that's why.
Yeah, that would explain it. But the number of times that they call AddMass is exactly the same, or it's close to the same that it makes no real difference. And here, okay, it's hard to see a big difference in the colors there. They're all very red and orange to me. The second one's probably the same. It's just a duplicate of the first, it seems.
Okay.
So there is. So we're still. Just click somewhere. No. Go back to system view. So the on the right hand side at the top, system view, and then select the bottom of the screen on the bottom of that panel. Yeah. So there's a variation, but it's maybe not so critical. So that's what I'm suggesting, that if we lose that information, then we'll have removed, well, the overhead of the measurement is based on the number of calls, which we know is the same for all of them, but that's still distorting the timings of everything else that's happening on that on those processes. Can we look at some of the other functions above it, the ones which are also taking some time? So calculate weights, for example.
Okay.
It has a similar sort of distribution of
Yeah,
type.
because this again for each particles.
So they're working on an array of particles that, or a vector of particles that has different numbers of particles in each process, but the number of times that they do this computation is the same.
Yeah.
Or it's very similar. But they're still, I'm still not convinced that we're getting any value from including those in the measurement. If we were to lose all that information and close up the compute moments, then I think we would still have the information we need and perhaps a more reliable set of information to analyze.
Okay. So maybe I could track this one, and I wouldn't really want to track the output, but maybe the particle, where the particles are moved, which is this one.
Can you not just exclude that add mass, and that would help you a lot, wouldn't it? Is that not just what you want to do?
No, I was excluding everything and keeping just.
Yeah, I mean, it works both ways. Either you exclude what you want to remove, or you include explicitly what you want to keep.
Yeah.
I would, I mean, it looks to me like add mass is the killer. I would just exclude add mass. Isn't that the best thing to do?
That's,
And then
you definitely want to exclude add mass, but.
And then rerun, and we might just rerun with just add mass excluded, and then we might get more reliable data because of the overhead will be just.
Yeah.
So I would just exclude add mass, and that would be all I would possibly do.
So you would track everything else?
Yeah, well, that's called 15 billion times, so we just have to get rid of it, and then we can look at what we're left with. I mean, I think that's the first thing to do. Just have to get rid of it.
Okay. Okay, now if I have to do so how do I don't remember, I need to check the slides. How do I I produce a summary with this filter? I don't know what I can.
Where's your job script? Inside the job script, you're going to set that file as part of it.
But before this, I wanted to have one of these output filter file, like is showing me. Even spell it wrong, but this this kind of file I want to see, no? Where it tells me exactly what I'm. So when there are these minus, it's because it's tracked, and when there are these plus, it's because it's not tracked, right? Well, it doesn't matter, maybe.
The minus is saying that it doesn't match the filter, so it's going to be included in measurements. And the plus is saying that it's matching the filter, so it will be removed. Christian, are you going to the breakout room with Katie?
Yeah, maybe in a minute. So I'm just chatting with Laura.
I think I know what it is. I think it's quite a straightforward error. I think I'll try and sort it. I might not be able to, but I think I know what it might be. So is that okay? And then I'll come back when I can't do it.
Okay. Yeah. By the way,
Okay.
we asked you to do a reference execution yesterday. Did you do that? One without
No, I
the
forgot. I forgot to do that actually. Maybe I can do it now. I really have to compute the code, to compile the code.
Exactly. You need to build a version without any score P involved and then run that so we have a reference time.
um, okay, this is finished.
You want to start again, or try again then, Katie, if you've managed to. Okay.
Yeah, it should work now.
It's very, very clunky. Breakout group. It's really annoying. There you go. Katie number 3.
Okay, this should not be a problem. Okay, so this is done. So
How
now
does this time here, how does this 117 seconds compare to your previous ones, the previous measurements?
it's about 80 seconds faster.
So all of that 80 seconds is measurement overhead that we just removed. Because it's doing the same computation, but we removed 80 seconds of measurement overhead. So it's now 80 seconds faster.
Okay, so if we go now, is there a way to, because I saw you were like, no, because this is is this scene like local file?
Yes,
Yeah.
you're running it on Archer, so it's in the local directory.
Okay, so I can open a new one.
Yes.
Which should be here, but it doesn't. No, it doesn't. Somehow it doesn't see it. I think I have to reopen a new window. But here I cannot. So let's do everything again.
And you're back to the same authority file problem, it seems.
Yeah. So let's remove them.
I think you'll have to remove it and log back in.
Yeah.
I don't know why it's I don't know what it's trying to do or why it's doing it.
I don't know if it's because I'm trying to. Okay, so. This one. And now we can see. Okay, so this one is the one where we track only. No, where we track everything but add mass. But I didn't check the score of this actually, so. I think we should remove still something else because it's 10 gigabyte.
Yes, 10 gigabytes is still a lot. So we had already had a, I'm curious, I would have expected it. I mean, we thought we were leaving 14 gigabytes and somehow that hasn't worked. So do the -r again so we see what's going on, what routines are there. So it seems to be suggesting 1.4 gigabytes for calculate weights. So, but I think all of these add JX, JY, JZ, PXX, PXY. I think all of those are things that I would also remove. Things I would exclude.
Yeah. Okay, let's redo this then. I would exclude everything, just add. Computers.
I would include gather moments as well.
Wouldn't
Include this
because
gather
like this is like this inside this, right? And wouldn't
the
if I
gather
include
moments
it,
is where the compute ghost is done, and I would also include the compute ghost. Sorry, communicate ghost P2G.
okay,
It's good to include at least those two additional ones.
okay.
And I think you were saying that particles mover is also something that's interesting and important.
So looking at the timing, yes, but I think that for the tracing, like now that I think a little bit, it's perhaps not so well. It's
I
when
think
it
you can include
communicates.
it.
I think would be interesting where it communicates. Which it should be somewhere here. Yeah. Maybe we could track where it communicates. Where it basically exchange the particles between the processors. Because the mover itself is just it just takes a lot of time because there are a lot of particles, but the operation is not. What do you say? Maybe this is the most interesting part, the communication.
Quite probably, but I see a lot of different things here, and it's hard to figure out exactly what's important and what's not at this stage. That's why I'm a bit nervous that you're selecting a few things that seem important, but maybe we're missing something.
Can we do like different in different moments to avoid to have like big files? Or is better to have a, well, we can try to include it and then see what happens. Particles move. Time. So I'm here with a colleague, and he would like also to ask a question. While I'm doing this, can he ask his question?
Sure, go ahead.
Okay, so I stop sharing so that he can. But you need to be enabled to share. Yeah. I think. So I stop sharing, and maybe you can share, and then I will reshare in a while. Okay. Okay. So. So I don't understand. No, but
No. Never mind.
okay, he changed mind. He solved this problem. Okay, so I will reshare my screen. This one matter. Okay, so go back to the other one.
So
Okay.
instead of using cube, can you try using square? Or you can use scorpy square. That's fine.
Okay, now it's reasonable.
That's much smaller. Yes.
Yeah. Okay. Okay. So
Instead of using cube, you use square.
yeah, it's just I need to. I don't think here will work because it's too much to have this terminal open. But let's try. It's not working. Okay, I need to exit login again.
So just use square and a dot. No profile, just a dot for the current directory. Yeah.
Like this? Okay.
Yes, that's enough. So it's going to look in this directory and look for a profile, found a profile, and it's now processed it into a summary file and bringing up cube to show that summary.
Okay.
Also, how did the time change for this measurement compared with the previous ones? I assume it was also a bit faster.
And much
That's
faster.
Yeah.
Yeah.
So,
Much faster.
and we've reduced the trace size or the measurement size considerably, but a lot of it was measurement overhead. and we don't have the same measurement overhead in this new version. But we still have all of the communication that's happening.
Yeah. So actually this routine is just for diagnostic purposes.
It may
So
be
this is for
diagnostic, it's taking
computation.
15% of your time, or 14% of the time is in that gather moments extra.
Yeah, I'm seeing that.
And that's including your initialization and everything else that was going on. So it's not just the solver, but that's 15% or 14% of the entire execution time. But maybe a small test case.
Yeah, but so well, normally, so now I'm saving. I'm dumping to file at each. It computes diagnostic at each time iteration. Because I have only 10 time step. Normally, I would do that every 100 iteration or so. So probably its impact will be reduced, but it still will be maybe something to think about.
So we're seeing that there is some MPI in there. We're seeing the send receives. We're seeing the barriers, but the majority of the time is computation time. It's not MPI. So that's where half of the time is spent in compute moments. Maybe you want to take a look at the statistics or the topology of the compute moments to see how balanced it is. So it's varying from 21 to 23 seconds. So, I mean, this was the function we were looking at before, I think, which was showing a large variation, but we've reduced it from, I don't know, what was it, 75 seconds down to 20 seconds. But the variation is still there, which the variation was exaggerated by the extra measurements, the extra overhead, but the variation is the same 10% variation, 5% variation.
Maybe it's worth to look at this.
So now you're looking at something that's taking very little time, so it's not so meaningful. Do you mean to look at the communication time?
Yeah, like to see if it was balanced, I wanted to check.
Okay, so now we're seeing the variation in send receive time. And then there's an MPI barrier there as well, which will also show it's a more regular pattern of imbalance, but there's definitely an imbalance there.
I'm trying to think why is that.
I think
maybe a sort of the particle could help here to balance the because the particles are never sorted.
Can we go back to the compute moments part, because that's where most of the compute moments was where the time was spent, the majority of the time inside gather moments.
Compute.
And then compute moments
here.
is there next to it.
Yeah.
Instead of peer percent, you can try peer distribution. Peer distribution will exaggerate things, so it's going from the lowest value, which is in this case white, up until the largest value in red. So it's showing you that the lower values, these greens and cyan, are those ones on the right-hand side, which might be on a different compute node. Is it the case? It's how many compute nodes are you working with? 4?
Two compute nodes.
Two?
Yeah.
But certainly those ones on the right-hand side, those processes on the right-hand side have less time, so they're faster than the ones on the left. But the ones on the left are showing a kind of spread from, I mean, you've got a mixed up pattern there of yellows and reds, and if you right click or hold the right click, you should come up with a.
I'm trying control. Usually the right click is control mouse, but it doesn't. Oh, what did I do? What should show up?
The right click should just bring up a pop-up, a panel that shows the actual values that you're seeing here.
Maybe this one.
Well, whenever you select it, the value changes at the bottom, so it's showing you the value that you've selected. Yeah.
Because the right doesn't seem to work on the Mac, so it's control, unless there is something here that I can use.
No, you have to use the right mouse button.
Which on the Mac would be just control and the mouse, but it doesn't work. No.
But when you do your click on the individual value, you see the value at the bottom of the screen, and maybe that's enough.
Yeah.
So what is the reddest one there? The reddest one would be about the 75, I guess. Well, it's 100%, but then the value below it is 21.9. Or no, the value below it is the average.
Yeah. This, okay.
That's showing the average and the standard deviation there.
Okay. Why are these less?
Why is there less computation time on those on the right-hand side?
Yeah, I'm trying to think.
It may be they have less particles to work with, or the particles that they're working with are simpler and easier to work with, or.
So because this would be like it's. Yeah, it might be that they have less particle. But it's strange because these are at the boundaries. So like at the boundary, there should be a lot. Things should be treated with care. So.
Gavin, are you referring to us? The 4 columns might be on a different node. Can we go back to the system view then? The system view will show us which nodes those all the processes.
Okay.
In the system tree.
Okay. How did you get rid of this? I don't remember. You did it in class, but I don't remember.
It was one of the right click button, the right click options to hide it. Or
which to me doesn't work.
Which is not working for you, I'm afraid. But
No.
If we scroll down, here we're seeing the first ranks, and those are all in the orange red.
Mm-hmm.
And as we go down, these are the same. So that's the second node. And we're seeing more greens coming in here.
Yeah.
So as we get to the higher numbers on that third node, there are greens. So there's only 3 nodes here, but the ones on that third node are the ones which have the greens.
Yeah,
the low value.
Yeah, the second node actually.
Actually, it's quite interesting. There's a change after 192. 192 is 3 times 64. I don't know if 64 has some meaning here.
So it would be the third socket because there are 2 sockets per node, right? Each node has 128 cores, but there are 2 sockets, isn't it?
I'm no expert on Archer, so I'm having to take a look myself.
There are 2. So I got chucked out the break. There are 2 sockets, yeah. But why do you care? It probably doesn't really matter for MPI unless there's.
We're trying to understand why the processes above 192 have much lower values for the computation time than the others.
Oh.
The sockets are fully populated, so the same number of processes, I believe, are running on each process.
Yeah.
And so, I mean, if they're all running the same number of processes, but some of the processes are faster, then the ones on that last process must have had less work to do or better access to the memory.
Sounds like a load balance issue. Can I see your Slurm script? Just
yeah, sure. I was already in the folder.
okay.
I
Fine.
killed everything up, so.
That's fine. That's fine. Keep going. Yeah. Okay. Fine. Keep going. Keep going. Yeah. 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 Keep going.
This is binding to the physical. Well, anyhow, with this, like,
that OpenFP's got nothing. The S run will bind your. So you're not using threads, so you're not using those, but the S run will bind. Your S run is binding. The distributed block does the binding. That's what does.
I'm binding to the physical cores, right?
Yeah, yeah, that's correct. Yeah. I mean, it does, given the huge comms time, it does sound like it's load imbalance in the computation, which is showing up as increased communication time because they're having to wait for each other. Is that not kind of?
The communication time is because of the imbalance in the computation, and that's why we were trying to understand why it is the computation time on that second socket is so much less. But it may be that they have less particles, they have less work to do, but they're certainly a lot faster.
It definitely looks like a software issue, not a hardware issue, I guess. But
just for curiosity,
what you could do, yeah, is
this should. Oh no, this doesn't tell us anything.
no,
because this is just a grid that I'm dumping. Or wait. No, nothing. This doesn't tell us anything because I'm dumping only the quantity on the grid. I can try to run. Maybe is the simulation itself. If I find a simulation which is more balanced, but though it's bit. So I expect the simulation to not be completely balanced because at a certain point there will be so particles will accumulate, but it should be kind of random and and periodic, if it doesn't make sense, because it's like a wave. So I don't expect that that everything is balanced, but the process at the corner.
But it's interesting that the last quarter of the processes are quite different from the first 3 quarters.
Yeah, definitely. And that's why I'm wondering, I should try, I think, with some other, like with a simulation where nothing physical should happen, and just with random noise, and see if this happen, if this also happen. Because if this also happen in that case, there might be some problem in the code.
Well, I don't know if how well you know the code, but I would just stick in a print, hi, I'm rank blah, I've got so many particles or something. That's kind of my approach, but.
To,
Of each process, write out how many particles it's working with?
Yeah, that's what yeah.
Oh boy, but this would be like, well, yeah, this can be done, but
Or is that already part of the output, that you have that information?
no, because in this case I'm dumping only the quantity on the grid, so like it's all interpolated to the grid. I'm not saving any particles data. Actually, I can.
I think you're going to get these X problems again. Did you get? Did you get logged out there?
What? Sorry.
Are you having to log back in again? Did your?
No, I just because
Oh,
oh, what I did now. Okay. It's just because I wanted to go into the code and
So every time you open a new window onto Archer and have a new login onto Archer, it's trying to create a new X authority file that is somehow conflicting with the first session, the previous session.
yeah.
Yeah.
I think that's supposed to be X authority 1, X authority 2, X authority 3, isn't it? And for some reason it's trying to do it in the same file as the previous. You've got 3, haven't you? Yeah. So the first one does X authority, the second one does X authority n for some unknown reason, and the third one doesn't have anywhere to go. Maybe.
So you would print this, but without basically the. So here it's just printing the 0, 1. You would print for every process.
Yeah, yeah.
Yeah,
I know which process it is as well.
Okay.
How many times is this function called? Every time step or something? Or
Yeah, this is called every time step. So we are going to get crazy with that.
how many time steps are there?
10. Well, not
Okay,
too
fine.
much. I can reduce the number of time step actually.
Yeah, that's fine. We want to know it. We want to know what's happening at the end. I get. Well, I don't know. I would guess we want to know what's happening at the end.
If you expect it to change, then we
Yeah.
can see how it changes. But what we're seeing in cube is the aggregate. So
Okay,
they're
of
all
course,
added
right.
together.
Should have used McMaster. Okay, so now we want to run this. Maybe we can. Well, let me run it here.
You've added this to the reference version that has no instrumentation. That's correct?
No, I'm running the one with instrumentation.
Okay, that's also
I
fine.
modified one of those instrumentation actually.
The one without instrumentation already ran?
Oh. I want to change it to this. The one without instrumentation. Right, basically it takes more or less the same time as with fewer traces.
Yes, so when you just were selectively measuring those 4 or 5 functions, it was 37 seconds, I seem to remember. So here it's gone from 35 to 37. So that's quite reasonable, but anything beyond 40, I would be very suspicious about that we're collecting too much.
It was 250 before, wasn't it? Or was that a different parameter set?
Exactly. When we were collecting everything, it was 250. And removing one function got us down to 150, I think, or so.
Yeah, and then like when we just selectively trace 3 function, it got to 37.
So is the job that's dumping out the number of particles running just now?
Yeah, this is here with the
The file?
instrumentation.
Yeah, so look at,
Those numbers are all very close, but that's only a subset of the processes.
yeah, can you less it or edit it or something? I don't know, or less it or. They're all the same, aren't they?
They're all close enough, and there's no big difference between the ones
Yeah.
above 192. So you have particles of different species, is that correct?
Yeah, because there are electrons and ions.
So you have two different species, and you
Yeah.
seem to have roughly the same numbers of both of them on each process.
I think so.
Well,
Oh, no, there are, sorry, there are,
I see three, four,
no, there are
four species.
four species in this simulation. I confused the setup. So there are two species of electrons and because they have different velocities. So
It's
there
the
are
same
two
number.
constituent plasma,
But
basically.
there doesn't seem to be any load imbalance in the number of particles. I don't know how many iterations is that, but iteration 12, okay, but I don't know, maybe that's not them.
So this is the fourth. I was curious to it was here. Okay, so for instance 221.
Yeah, no, it's all fine, isn't it? What are your boundary conditions on the box? Are they periodic or non-periodic?
Periodic, is everything periodic? For instance, this is very this is the processor that according to this doesn't do much. 251.
At the moment, you're looking at send, receive, replace in the middle.
Ah, yeah.
You probably want to select the compute moments. Further down,
Yeah.
compute moments. Is it not the compute moments that you want?
Yeah. I just.
That's
Okay,
where we
so
see the dramatic difference. The last quarter of the processes have much lower values than the others. I mean, we're looking at an exaggerated distribution here, so it's not so pronounced, but it's certainly consistent across them.
and then those processes translate into high communication cost, does it? Is it the inverse for the communication?
Those
you look
ones
at the
that
heat
have
map.
less time have more time waiting in the communication, yes.
Right.
Although the pattern there was also interesting. Can we go back to the topology? Because the topology gives us the oversight.
For this,
For that,
for
for that, yeah, for that one.
for the
So
for the
for send-
compute moment.
Well, we've seen that one. It's all green on the right. So do the same for send, receive, replace. Okay, so it's very extreme.
And then for the barrier,
Oh, you still have the barrier.
that one's kind of weird. I mean, that certainly suggests that you have blocks of 4x4 somewhere. Or maybe it's just blocks of 2x4, but I see. Is this the version where we removed the extra barriers from it, or this still has the barrier called after each of the directions?
I think I reverted to the original version because
What
we saw
is
that it
weird?
didn't make any difference.
Or maybe MPI send receive replace isn't that slow. I don't know, but it isn't that. I don't under what I'm trying to say. I would have thought with barriers, then you'd have thought that. Can we look at the load balance in MPI send receive? Yeah, well, if you've got barriers, yeah, you go back to send receive replace. And this doesn't make any sense because all the processes are doing communication at exactly the same time. So, it's quite a complicated communications pattern because it's doing diagonals. It's doing 26. I think it's doing 26 comms per process, isn't it? All the faces, all the edges, and all the corners. 6 faces. How does it work?
No, can you repeat the question? I didn't hear. Sorry.
Well, I just looked at the code for 5 minutes, but it looks like it's communicating to all the neighbors, including the diagonals. It's not an up, down, left, right. It's communicating the corners and the edges of the local domain.
Yeah, because so this is for the field solver. So there are quantities that are defined on the edge of the grid and quantities that are defined on the center of the grid.
To me, it looked like it was doing diagonal communication. It looked like it had a huge number of communication calls.
If we select the visits metric, we'll see the number of calls, and it's presumably the same for each process. But that doesn't. Yeah, I mean it's white because they're all the same here. So there's no variation across processes. But I think that's what you'd expect from the periodic boundary conditions. That each process is talking with 26 neighbors, is exchanging 26 neighbors, and the amount of data that they're sending is probably also the same in aggregate. Or is the amount of data related to the number of particles that they have, or the particles that you have to transfer?
Yeah, it is because of the in a certain sense it is, but like since they are like all balanced with the particle, I don't expect and I don't.
Can you select bytes transferred on the left pane, the left metric tree?
That's a good one. That's a good one. Yeah.
So there's no data transferred in the barrier. We need to select point to point, or yeah, it'll be point to point. We need. Sent. So they're still all the same. So they're all white on the right. They're all the same.
It's the faces of it's the faces and the edges, whatever the grid. So
yeah. But they're sending exactly the same amount of data, so it's not. I mean, they have close to the same numbers of particles, so it's not too surprising. But they're exactly the same. So it's exchanging vectors of a fixed size.
Yeah, because the buffer is fixed. So the buffer to send is fixed, and only if for certain reason, like imagine the number of particles becomes too big, then it does a resizing. But in this case, that there were no it would have output the resizing. It doesn't, so there is no resizing. So it's sending the same buffer.
Mm-hmm. So some of the buffer is empty or doesn't include particles, but it's the same size of buffer that's transferred.
Yeah. But I expect that more or less the number of particles that has to be transferred is more or less the same, because it's for this simulation step.
Not transferring particles though, is it? It's transferring the interpolated data that's been interpolated onto the grid, isn't it? I mean, it's a regular grid.
No, it transfers also particles.
So how are the?
It'll be the particles
someone-
moving.
okay.
Particle com 3D should be there. Well, I don't know IPIC actually too well, but it should have like, that should be the same. So particles, and it should be here. I need to check on this point. Let's see. You see, here is where it communicates. Where it does the communication. It should be the same in IPIC. Which is not here, but yeah.
There'll be no imbalance inside an MPI routine. You need to select one of the computation routines in the middle.
Okay, so like,
And then you can select overload on the left-hand side. Okay. So the ones in non-white here, the ones in blue, are the ones which have extra work, which just means more than the average amount of work. And the ones which are white would be the underloaded ones, which you were previously seeing in green. I mean, it's interesting that the first 64 and the second 64 are all very blue. Then you've got a sort of intermediate regime for the next 64, the next 4 columns. And the last 4 columns, there's only just one that has a slightly overloaded amount. So there's quite different, I mean, there's a difference between the first node and the second node, but also between the first and second socket of the second node in terms of the amount of time that they're taking for the work.
And also the particle mover is like this, which is very strange.
But I mean, you have to be careful interpreting what you're seeing on the right-hand side here, because there's always going to be something that's slightly higher and something that's slightly lower, and anything that's slightly above average will be considered overloaded. That's why it's worth judging from the pane in the middle how much there is. So what's shown in orange there with the compute moments, that's where a lot of the overload is. But for the particle mover, it's very small. There's going to be some, there's always going to be some, but it's very small, so it's negligible in the scheme of things. And for gather moments, was it the same or was it different for gather moments? Or gather moments extra, that's the other thing is.
Gather moments extra.
Sorry, just can you paste the URL of the GitHub, the public GitHub? I seem to have lost it. I had it.
Yeah, the GitHub is.
CMPA.
It stands for Center for Mathematical Plasma Astrophysics. And I lost the chat here.
I've got it. It's okay. Oh yeah, yeah. So the only send, receive, replace I can find is in ComBasic 3D.
So this code I picked 3D is not exactly the code that I'm using, but if you are interested, we could like
okay, so I picked 3D. It only does regular grid communication. It doesn't do anything with particles, as far as I can tell.
No, it should do as the particles.
The only MPI send, receive, replace is on a grid. I think.
Yes,
Actually, maybe not. Okay, maybe I'm wrong. Actually.
yeah, it's a bit strange because it should communicate also the particles.
I think I may have got this wrong.
But I mean, this takes 1 second to we can actually. So you won't find this function like that we are profiling because this is proper of XIM, these gather moments. But the rest will be similar. So I'm curious just to if, So I'm just curious to see. So this is what I set up is a very boring plasma where nothing should happen. And I'm curious to see if we repeat this exercise, if we find also this imbalance.
Do you have a 3D grid or a two? So is the processes arranged in a 3D grid, and we've displayed them as a 2D grid that you folded to the axes? Is that right? The print.
So the code itself is inherently 3D, but basically, like what we do is we just place basically one point on the third direction, so it becomes 2D.
Okay.
Ah, I know. Exactly.
But the code itself, the code could cope with a 3D grid. Is that you're just choosing to do a 2D grid, a 2D decomposition?
Yeah.
Okay. Okay, so my statement about diagonals isn't true for your decomposition.
So did I see that when it started, they all had exactly the same number, but now after a few steps, they're slightly different?
Yeah. So when they start, this is like it initiates the same number of particles.
Yeah, so they're all starting off with 409,600.
Yeah.
And then after the first few steps, that it
Yeah,
has
because
changed,
so
but it's not changed dramatically.
So what happened is that these particles, so they are initiated with a random velocity. And so at the first step, their position gets updated with this random velocity. Does it make sense?
Yeah. I mean, they just
And
randomly
so
move
they move.
around, but
Yeah.
so there'll be some fluctuations in terms of spreading out and varying. there's, I mean, so eventually you could expect there to be, well, in this case, there shouldn't be any clustering or convergence to one corner or one part of the domain, but from the other simulation mode, maybe there could be, but here it should stay roughly, I mean, it should just be a noisy balance.
Yeah, that's what I expect in. So in the other simulation, I was modeling like a plasma wave or instability. So like it could have happened that there were like places with more particles, like but I was expecting that it to be to have a periodic structure, not to all the process on the right. But now I'm just modeling a really random noise, so nothing should happen. That's why I'm curious to see how it's compared to this one. And this should be done, right?
Okay, so it finished.
Okay, because this is the first time we are doing it. So now if we do okay. So we track the same.
So just, I was looking at the output there. It's doing some Maxwell solve to some tolerance. Yeah, is that solving for the electromagnetic field or something?
Yeah. So
presumably that's an iterative process.
it is, because it's a GMRS solver.
So that will be doing the halo swaps on the grid, won't it? That will be doing the.
Yeah, the field solve. I mean, that is like in the.
So I think that'll. I think that'll absolutely dominate the. I would have thought it'd totally dominate the communications compared to moving a few particles, because you only move the particles every time step, but you do the halo swap for number of time step times number of how many GM-res iterations. I don't know how many GM-res iterations it takes you, but over tens or 20. I don't know how many it takes. Does it print it out? But I mean, anyway.
So to be honest, I'm now using a version where the solver is similar to the one in IPIC 3D, but which is not efficient. So like since a couple of years ago, there it was implemented. So before I joined actually the group in Leuven, it was implemented a solver using Petsy.
Right.
So which is we should do that better. But I'm not using Petsy at the moment. So
both the routine that swap the use MPI send receive replace for swapping the faces of the grid and for exchanging particles. My guess is that the communication is utterly dominated by the faces, that the particles is done once every time step, and that's just not, I just think that, I think the communications we're seeing, my guess is that if we're seeing it entirely from that, my guess anyway, I don't know. I still don't understand why that is load imbalance. It seems.
So we are not tracking data. So what we are tracking is just routine about the particles. Because
is that capturing most of the time? Is that capturing all the time or not?
Can you repeat the question? Sorry.
Does that account for the majority of the time then? So I keep forgetting I'm not looking at the code that you're running. Sorry, I keep forgetting that code I'm looking at is not the code you're running. Sorry.
But in a certain sense, it's very similar. So there is the MPI, like how to say the MPI. So the communication where like we recycle from that code actually.
Yeah.
We just changed.
But presumably a very high level. Because I'm guessing here that the code spends almost all its time in doing that Maxwell solve. Is that correct or not?
No, actually, so okay, that is why we focus on this in this routine. And for me, they were not a surprise at the beginning because okay, this one, the one that I forgot to create. Okay, this would have to finish. So, okay, this is done with the MPI whole time, the command, and like if you look at this, this is where the field is computed because the number of the time is very small compared to the other because this only depends on the grid point, while there are billion of particles. So everything that concerned with the particles.
Fine, okay. You have quite a coarse grid. Okay.
It's not that it's coarse. Like I mean, the simulation is as the dx and dy are quite fine actually, but there are simply smaller points compared to the number of particles. So whatever is dominated by actually this function here.
Right.
I might actually have also a representation. So
do you have the has that finished now? Do you have the score P output from that? The one that's just finished?
yeah, I think so. Yeah. Now,
Is it still running?
No, it's finished. If I do square, just this I have to do, right? I think so.
Yes.
Hi.
Ah, if I put a 9%, will then free my? Will that
Yes,
work?
it
And
should
free
work,
my?
yes.
Okay. So I have the things.
Single participant is just where it's looking for a special
Oh, no.
process, like a process, or so it's just a specialization of overload that is only looking for single processes.
So it's the same pattern, even if this simulation should be more balanced.
That's interesting. So here you believe that it should be very balanced, but we're still seeing a very significant difference between the processes on the first node and the second node, and specifically
How
on
are
the
the
second.
axes done on that? Which is the fastest moving axis? Where's rank 1? Is it on this map?
I believe it's the top left corner, but
Rank 0, no, rank 1. Rank 1 white or blue?
top left is blue.
Is it this one?
That's the one I believe.
No.
If you go to the system view, it will show you that one. That's
Rank
rank 0.
0.
So that one
Okay, so go
has
back.
that one has a little bit more work than the others.
I'm just trying to work out how the axes go to try and work out the mapping between nodes and things. Maybe you worked it out before, but can you go back to the topologies? So click on the white one to the right of it. No, just no, the other, just in the top left-hand corner, but
No, could you repeat? Sorry.
at the very top left-hand corner.
Top left is blue.
And let's go one to the right now. Just one to the right.
Ah, this one. Okay.
So is that guy 1 or 16? That's what I want to know. That's what I want to know.
I believe it's 16.
Okay.
In the system view, we'll see it's 16.
Yeah.
Fine.
It
Okay.
is.
So it's going down the way. Okay, fine. So you're so okay. So go back to the topologies. We're at four nodes here. Yeah.
I closed the window because 1 second. I'll be back.
There are 2 nodes, don't we?
It's 2 nodes.
Yeah, sorry. Doesn't make any sense, really.
Take a screenshot of this.
Elisabetta, can we try a new measurement with the score P metrics that I've pasted into the chat?
Yeah, sure. Just need to find it. Okay, so would you do this for this simulation for the thermal plasma?
It probably doesn't make any difference because we're seeing the same issue in both of them.
Yeah.
So whichever.
You just pass. I just need to include it here, right?
Exactly, that's perfect.
Okay. And the rest is the same. So, can you remind? So we have seen a bit of this, but not much today. What does this? What are we tracking here?
So these are some additional hardware counter metrics. So the first one is total instructions. The second one is total cycles. So we'll see how many instructions are being executed by the different processes in the different parts. If it's completely the same computation, we should see exactly the same number of instructions and the same number of cycles. And then the last 2 counters there are ones which are specific to the AMD processor, looking at stall cycles. So where it's stalled on the front end side when it's fetching instructions or fetching data, or on the back end side, which is where it's processing data and storing results. I don't know the exact hardware definitions here, but those just are some high level counters to give us some idea if it's maybe something happening at the processor level.
Okay.
For example, if the second node is slower accessing memory, we should see that in one of the stall cycles counters.
Is this something to do with the fact that I mean, do you suspect something to do with how the because AMD processor, they assess memory a bit differently, right?
I really don't think it's a hardware thing. It's very unusual to see anything of the hardware reflected in an MPI program. So
It's just something to try and rule out.
no, it's definitely right. So I would like to do, there's only one. The only time I've seen weird effects is, give me a second. Who is slow? Is it node 0 that's slow or node 1?
Node 1. It's a
Node
high
1.
rank, 192 and above. So
The
they're all
only
on
time
over the second
I've
rank.
behavior is when rank 0 allocates an enormous array and actually uses up all its memory, and so the other processes end up on the wrong NUMA region. But that's very rare. That would only happen on node 0, so that's not the problem. So yeah. Okay, I think it's.
So you keep getting this question, never ask for updates. It keeps coming back.
Yeah. And somehow, like, I cannot, it might be something related to the Mac or something. I cannot move it, move the window, so it stays there. So what do we want to see here?
I'm wondering whether we see the same load balance across the different threads or processes. So they're all more or less exactly the same, completely balanced.
If I do this again, would...
Well, it's showing there is a tiny variation, but the variation is negligible. Go to the peer percent instead of peer distribution. Peer distribution will exaggerate any difference, but here they're all red to my eyes, and that's instructions. So they're all doing the same number of computations or the same number of instructions. And when we look at total cycles, I would expect the total cycles should correspond to what we're seeing as time. So below what you've selected as total instructions, we have total cycles, and that's completely uniform as well. And when we go down through the next two counters for the stalled cycles for front end, back end, there's one that's red, but it's probably not so serious. And for the back end, which is much higher anyway, everything's red there. So there's no difference at what's happening at the hardware level. They're all executing the same number of instructions, and they're all taking the same amount or they're all having the same cycles and accesses to what they're working with. So we still have the time difference if we're back to the time menu.
Okay.
So there is a tiny difference on there's still a difference on the 192 and above.
So actually, is it significant? I can't understand that.
Well, the green ones are kind of, well, the best thing is to go back to the system view and look at the distribution in the statistics. Or here you're looking at the individual node values, but so there's a variation of at least a second there between the ones that are at the low end and the ones at the high end. And a second of variation or 10% variation seems like a lot when the number of particles that's different is very much smaller, and it didn't look like there was such a pattern to it.
There is maybe try, give me a second, I'll just find it.
Was it better? Can you select one of the stall cycles metrics on the back end stall cycles, I guess?
Yeah, the button. I'm just taking note of what we are discussing, because I would like to discuss then with the other people that work on the code.
It's actually, I was wrong that it's unlikely to be a hardware issue, because there are some funninesses with MPI. So could you rerun with? Does this have all the same metrics as before plus other ones? Brian, I wasn't paying attention. You can see the load imbalance on. Oh, that's what you're seeing there, isn't it? That's load imbalance on what? You're right.
Well, here we're seeing the variation of stall cycles, but
yeah.
It was in the time, or if we go to total cycles, it should be the same as time.
Right. If you look at send, receive, replace, you still see that the weirdness there, that it's all very different.
When we go to send, receive,
Can't remember if this was taking a lot of different time.
Here we were not seeing.
There we're seeing a variation as well.
Yeah.
We expect to see a variation across the processes. And the topology will show us the ones on the right-hand side have the higher times in the send receive, but that's not so unexpected, I don't think.
That's huge, though, isn't it? The difference was an order of magnitude, wasn't it?
No, it's probably not so well. I mean, an order of magnitude between 0 and a small number is still quite a lot. Because this is the waiting time in the send receive, or well, it's mostly waiting
the
time.
Absolute time? Sorry, maybe I misread it. Do the absolute time, not the pure percent.
The absolute time show like no imbalance. I mean,
you had the box plot. That was the box plot which I was interested in.
Yeah.
Yeah, there's quite a variation there, but it's between a low value and a not so low value.
I can't get a feeling for the actual. I think we should maybe rerun. Does this run show that weird, a quarter of the process is on the right doing funny stuff? Any of these plots. So I don't know if we've taken out metrics or just added them.
So the metric that was showing that was the time metric, or the imbalance metric, yeah.
Yeah.
Both. I mean, the overload is based on the time metric.
Okay. Fine. Okay. Fine. And that's pretty dramatic, isn't it?
It's very clear that there's a difference there. Yeah.
So there could be a problem with the way the MPI is working. So in your Slurm script, could you put this? I'm gonna.
Yeah.
That's two. So you can use a different MPI. So just before you do the S run. You can't, yeah, some anywhere, funny, but just stick those module swap in.
But
Anywhere after the last module load, do that module swap stuff I've got.
what should I do? So, did you
It's in
put
the
it in
chat.
chat? Okay, sorry, I didn't see. This is about the
The MPI version, basically. Try that. Just to eliminate this, I mean, because it looks very weird. Yeah. So, yeah, try that.
Is this what is this like? So I know these options show up like when you try to compile MPIC, for instance, but I don't know what they are.
Basically, at the very lowest level, it's saying there are two protocols for transferring data across the network. One's called Open Fabrics Interface, which is OFI, and one's called UCX, which is something else. So it's just at the very, very lowest level. What protocol does it use for transmitting data over the network? For reasons we don't understand, they have quite different performance characteristics. So just to eliminate it, it's just interesting to see if you get it. Try rerunning that.
Did you notice like different performances with I want to
Not normally with codes that do point-to-point communications, I have to say. It's normally codes that do collective communications, but it is still interesting to. Can I look at the top of the file just to check that it did do the right thing?
Yeah.
Can you less it or VI? I don't know. Okay. Oh, where's the output?
the output of what?
So you had
So
other
these
things
are
like
things that I print.
it doesn't seem to be. When you do module load, you should get output and things, shouldn't you? So I'm surprised it hasn't.
It goes in the error, I think.
Oh, okay, fine. Okay, right.
I don't know for which reason it goes to the error.
Modules are outputs to standard error is totally stupid, but it does. It's a complete nightmare, but it does. All the module commands. So scroll up a bit.
Yes. No, open it.
Yeah, I think it's probably okay. Anyway, I think it's probably okay. Did it finish?
Yeah, you should have. I never noticed that it print also this in the error.
Okay, can we look at the plot, the output from score
Yeah.
P?
Okay.
I think it's getting confused by the fact you have multiple logins and some of them are on different nodes. I think that's the problem.
I just want to keep everything open if we want to go back.
Yeah,
So that's
that's why the X isn't working correctly with the combination of multiple sessions, some of them on different nodes. It's just getting very confused, unfortunately. So
yeah. Yeah, probably the best solution would be to install it on locally and then copy the file, right? But
okay.
Still similar.
Okay, so okay, so that didn't make any. Okay, fine. That was okay. That was useful. It didn't really. Okay.
Did it change the overall performance much?
I don't think it did. It was like 28, which looks very similar, but
19 seconds, and the other is yeah, no,
Yeah, very similar.
yeah.
What is the second number? You've got a 19.6 seconds and a 39.
So this comes from the code. So this is encoded in the code, and this is just in my bash, in my JavaScript. So it's just a
So it's timing the S run itself, so it'll include
yeah,
the startup costs.
exactly. Yeah, I wanted
Yeah.
to show the JavaScript. Yeah, you see, is this just?
Mm-hmm.
So it's different for this
Yeah, I mean, the startup costs for the S run can vary from run to run quite substantially.
It usually this maybe because like usually I do bigger run, I don't notice this big difference. Here there are quite a lot of, I don't know.
Yeah, I mean, in a longer run, then the few seconds of difference won't be such a big deal.
Yeah.
The S run cost will depend on how many nodes it has to start up and wait for them all to finish. So if you're running on hundreds of nodes, it'll be much longer than if you're just running, in this case, on 2 nodes. And 1 node is probably faster as well. But it's not under your control. You can't control how quickly this run starts up, but it's 10 seconds or 5 seconds that's going to be a difference.
So the other thing you could try is just to try and tease out this kind of, I don't know, socket node thing in your batch script.
Yeah.
So, oh, I can't do nodes equals 4.
So,
Tasks
so
per
you want?
node equals 6.
Ah,
Tasks per
okay.
node equals 64. And that will just use the first. That will just use the first socket on each of 4 nodes. Different. We'll just see if we see anything. You know. So yeah. So we'll see if we. But it is weird, right? You're right, Brian. It is very weird that it corresponds to the. It doesn't give you anything in the simulation which corresponds to the architecture, but the the timing seems to correspond to the architecture. It's very weird. Did that run already, or?
Yeah,
Sorry.
it's this one.
I have to go. I've got to. I'm on the help desk at the moment. I've got a query, but
I have to pull this one to see, and we want to see. So now it seems that
now it's the first node.
Yeah, when the first node hasn't changed, first socket hasn't changed.
I understand. Is it significant, or?
It's a lot less now.
I'm afraid I have to go. I'll be back in a second.
what is this zero MPI file operation? I didn't notice it before.
Well, it's one of the hierarchies that Scalasca has, the square post-processing has produced. And since you're not using MPI file operations, then it's showing that you're not using them.
Mm-hmm.
And these metrics that you're looking at the moment with the computational imbalance, those are also generated by the post-processing. Can we see the range of values that for this new measurement? So either the time or the computation time. We can use one of the other metrics, but it's better to stay with time, I think, at this point. But you need to close it so that we have close the time metric so that we have it all. And then in the box plot perspective, we'll see the range of values. I'm wondering if those are different from what we had before.
Do you want
statistics?
Okay.
Statistics too.
Okay.
So this 12.19 to 12.41, this is a lot better than we had on 2 nodes. Although, from what I remember on 2 nodes, it was between 10.75 and 11.75. So it's got slower.
Oh no, it's still responsive. Okay.
We need either
What
select compute moments or you have to collapse it.
Yeah.
And actually, it's better to select the compute moments because that's what we're seeing. We're interested in the variation of the compute moments calculation time.
Yeah, but somehow it's not responsive anymore. Okay.
Oh dear.
Yeah, but I can open another.
Okay, so here we're seeing 10.5 seconds to 11.3. That's on 2 nodes, as I remember.
Yeah, this is in 2 nodes. And this is in 4 nodes. So yes.
This is more gather moments. So we want to go inside gather moments and just select the what is it, calculate moments or something?
Compute moments.
Compute moments. So on 4 nodes, it's slower. The fastest ones are slower and the slowest ones are slower.
Yeah, it takes more time. Yes.
Which is, in my mind, strange, because on 4 nodes, you have, I mean, it's not using all of the cores on the 4 nodes, but you don't have competition for memory or anything. So there's nothing that explains to me why 4 nodes should be slower than 2 nodes.
But it could be. So we should get the same number, right? But I mean, this is due to maybe statistical fluctuations, or we didn't get the same nodes, I guess.
Well, with 4 nodes, you'd have different nodes from when you're on 2.
Yeah.
That's for sure. But I wouldn't expect the specific, for a purely computational part of the code, I wouldn't expect the nodes that you get to make any big difference. And the fact that you're only using half of the cores on the node should make things faster. It shouldn't make things slower.
But when I don't fill the node like this, maybe it would be. Maybe I should put CPU per task too. So it takes the, would that like take one and then one empty and then one and then one empty? Does
It would, yes. Although I think that what David was saying was he was hoping that by only using 64 cores, you would only be using the first socket. So the first 64 cores on the node would be used, and not the second 64. Having, if you say 2 CPUs per task, then it will be using every second CPU, but it will have to use both of the sockets in that case.
yeah, but it will be more balanced, no? So maybe it's because it's not. I don't know. It's just like a question. Like,
it's definitely a legitimate question, and it would again be using both of the sockets, but only half of the cores on each socket. And using half of the cores on the socket should definitely make things faster. So yes, I mean, it's worth trying that configuration as well. You putting 2 CPUs per task. Then we should definitely see that the 4 nodes are faster.
so what if I put also? But this I don't remember. I have to check in another script. Here I put the map, the exact map that I want. But I need to check. I don't remember exactly how to do. I have to check in another script. Let's see. So if I put this instruction, which I'm not sure it works with srun also, but
yeah, that's what I'm not sure either. I haven't mean, you can
Because
certainly
if
try
I
it.
do, but maybe we could do with MPI run. MPI run.
Oh, now we're changing a lot.
No, okay. So, okay. Maybe I can try this by myself and because with this we are sure how to do the bind, how to we are mapping, right?
I mean, you can try and see if I don't know if Estron accepts that argument. What was it called? It was map
So
bind.
This would be basically the number of processor that you want in a node spaced by 2.
Yeah, but I'm not seeing that as an option that Estron accepts.
Because this is something of the MPIC or the open.
Exactly. I think it's an option of a specific MPI that's not necessarily
Yeah.
supported by Slurm or by Cray MPI or
Yeah,
whatever is
maybe,
available here.
yeah, maybe it's not worth. Okay, let's do it like this. Oh no, I want to change also the. Oh. Much faster. I mean, not much faster, but 15 seconds instead of
Yeah, but
19.
significantly faster, yes. And that's what we expected, but you're using every second core.
So he's spacing them out now on a node rather than packing them.
Exactly. When we tried to use, when we did what you suggest of only using 64 per node, that actually was slower, which doesn't make sense to me. So now we're doing a reserving 2 cores per process. We're spreading them out across the node, and that has been faster. So that makes sense. I mean, we only have half the number of cores on each node accessing the memory.
Yeah,
That's going to be faster.
Yeah.
But why having them all on the first socket and leaving the second socket empty? Why that would be slower?
Well, you have a lot more. We have a lot more inter-node communication of the network there because we're using 4 nodes, not 2. So that might have had it.
Yeah, the communication can be slower for sure, but we were looking at the purely computational part.
Oh, sorry.
The computational part was slower.
Oh, the computational part was slower. Okay, that doesn't make any sense. It doesn't make any sense. It's all very weird, isn't it?
But at least we have something that makes sense, that by only using half of the cores, it's faster. I think we're still trying to see if the pattern has changed.
I'm afraid I've got to go now, but thanks. thanks for the course. It's been very, very useful, very enjoyable.